So we've done this before. The Euler's second law has an extension of Newton's second law for rigid bodies to take care of the relationship between the moment and the angular momentum. So the form that we looked at was how the things are related as far as angular momentum is concerned, but there are certain other forms of the same which are useful in certain other problems, in particular how it is related to the angular velocity. So whatever the torque that you apply, how does that change the angular velocity, and that can be very, very useful in certain problems, especially in aircraft dynamics, and therefore we will take a look at a few alternate forms of the Euler's second law. So throughout today's class, we will be using this Euler's second law quite a bit, so I'll just abbreviate it to E2L. And as a part of this whole process, we'll be introducing the concept of the 3D inertia matrix. You've seen parts of it already in terms of the components like the moments of inertia, etc. Now putting them together for a full 3D problem in terms of a matrix, and how you can actually transform it using some of the angles that we already considered early on, right? Yeah. So now this is done and dusted as far as Euler's first law is concerned. It dealing with forces and the rate of change of translational momentum. So we'll not touch upon that as of now. We'll focus on the rotation. Most of the class today will be looking at 3D and looking at 2D sometimes as a special case. Okay, so as always, I'll put the result that we want to get to in the slide at the end. Sometimes it could be an intermediate result, but it's essentially a result of that particular slide. And as I said, the whole purpose of today's class is to look at alternate forms, and the first form that we will look at for the Euler's second law is the angular momentum form, which you're already familiar with. So it's just more of a review, recap, so that we can see how we can get from there to the other forms that matter to us for certain problems. The important point to note is that if you take an arbitrary point P, then you take the torque about that particular point, you will not get the rate of change of angular momentum about that point. We said that it's actually something that is valid, this instead of not equal to, only for two special cases. We'll just review that over here, right? So the Euler's second law for a part, either you consider a rigid body or a particle set, because we went to the rigid body, remember, from a particle set, because we said that we can actually consider a rigid body as a set of particles with certain additional constraints in terms of the distance between any two particles always being a constant, right? So that kind of defines that it's a rigid body, because bodies in reality are flexible. Some are more flexible than the other, but everything flexes, and essentially the distance between 2 points changes, and that's what we measure as strain, but that's for another course. So right now we are focusing on rigid bodies, and therefore it is important. Now, as we said, this second law is a little simpler in terms of the angular momentum about two specific kinds of points. One is, of course, the point which is fixed in the inertial frame of reference. And for example, a point fixed in the inertial frame of reference, we said that it could be any point on the axis of rotation for a rigid body. So that point we typically call as O. It could be the pivot point fixed in an inertial frame of reference as well as the rigid body, but it's not its CM necessarily, that is the center of mass, because in the case of the CM you get additional simplifications, and therefore we are not considering that. So any point, for example, on a fixed rotation axis which is not passing through the center of mass would be a point fixed in the inertial frame of reference. Another point for which E2L simplifies, Euler's second law simplifies, is of course the particle sets or the rigid body's center of mass. And this is the reason why we are putting that separately, because in the first case we want it to be fixed in the inertially, in other words, inertially fixed, it is not moving at all, whereas when you're taking it about the CM, the CM can be moving. So in other words, we take E1L, that is Euler's first law, in conjunction with Euler's second law. We consider the translation as well. When the center of mass is moving at a certain velocity, its mass comes into picture as well, right? So keeping that in mind, remember that depending upon the specific problem, sometimes it's more convenient to take the angular momentum either about a fixed point or about the center of mass. In particular, when you're dealing with aircraft dynamics, for example, and you're dealing with the acceleration of the aircraft, probably it's performing certain maneuvers, etc. Many a times more convenient to use the center of mass over there, right? So now the equations look innocuously similar. Both of them are saying that the torque that you apply is essentially the time rate of change of the angular momentum, and both of them are time rates of change in the inertial frame of reference, which is why we see pre-superscript I before the d by dt, right? But very important to keep in mind the importance of these subscripts, that when you're talking about the torque, you're taking torque about a particular point, and similarly the angular momentum is also calculated about the same point. In one case O, which is the inertially fixed point; in the other case it is C, the center of mass of the body, whose motion, in particular rotary motion, that we are focusing on over here, right? Now these two are related to each other, and which is why you can actually, if you know one of these equations, you can prove the other equation as well, because you can essentially take it from the fact that you have a vector whose time rate you want to determine in two different frames of reference. You can usually do that. So similar kind of a thing we are doing here, but here we are taking the definition of the angular momentum itself as a cross product of r with the translational momentum. So the r cross with the translational momentum of the body over here, and the translational momentum L, remember, is something that is not going to change depending upon the choice of point, this O, C, etc. The choices are essential only for the angular momentum or for the torque, not for the translational momentum. So all these three terms will have a cross L, and the only reason they differ is in terms of that position vector, and by the fact that you can take from an arbitrary point to O, the position vector can be thought of as the position vector from that same arbitrary point to C, and then from C to O. So from that you can essentially derive this equation. So this is essentially the relation between the angular momentum of the same body at the same instant of time, one taken about the fixed, inertially fixed point, the other taken about the center of mass of the body, and they differ from each other by means of this particular cross product. So it's the distance between that inertially fixed point and C matters, as well as the translational momentum matters, and also their directions matter, because you know that this cross product can sometimes go to 0, in which case those two can be even without R and L individually being 0, right? So the other important thing is the second law, when it's Euler's second law, that is, where can't be as easily written for points other than O and C, that is, other than the inertially fixed and the center of mass points. So for general case, we see that it is essentially, by definition, it is essentially R cross the translational momentum, which is rate of change of translational momentum, and if the mass is not changing, it just becomes the rate of change of the velocity, becomes the acceleration, and this is what you end up with. So whereas this is equal, where this is not equal, and therefore, because what is within this integration cannot be thought of as a time rate of change of the angular momentum about P, right? So that's as far as the angular momentum is concerned, and the relationship with the torque is concerned, which is what Euler's second law is all about. Now we get into talking about the rigid body's angular momentum about the center of mass. So it's essentially that first case that, second case that we looked at in the previous slide, we want to take it a little further, and we would like to show that this is what it is. You have seen flavors of this already, so it's just that most of it is a recap, but we want to set the context for today's purpose of taking the Euler's second law from an angular momentum perspective to an angular velocity perspective. Okay. So once again, we take a certain chunk of the material, which is an infinitesimal chunk around a point Q, which is a part of the body, and let's say the mass of that infinitesimal element is dm. So we've been using this consistently, this notation. O always refers to a point inertially fixed, C always refers to the center of mass, and Q always refers to an arbitrary point within the body, within the rigid body, around which this infinitesimal mass element dm is there, right? So now we know that the translational momentum of that particle or infinitesimal mass is essentially its mass times its velocity. So that's dm times vq, and we are taking the pre-cross product of that translational momentum of that infinitesimal mass with the position vector from the point about which you want to take the angular momentum, namely c, to the specific point q. And so both these terms, rcq as well as vq, are functions of the particular point, because both depend on q, and therefore both are within the integral sign and cannot normally be taken out of the integral sign. Now we get to use the velocity at any point of the rigid body is known in terms of another point of rigid body, namely its center of mass, and the angular velocity of the rigid body, omega. So then this is the standard formula you've been using quite frequently in all of your homeworks, so that the velocity of the point q, which is an arbitrary point in the rigid body, is given in terms of its center of mass's velocity, the rigid body's angular velocity, and the position vector from the center of mass to that arbitrary material point, right? So now we can substitute for that vq over here, and then we can carry out that integration. And in fact, we have seen this before, that the first term goes to 0, not because vc goes to 0 or rcq goes to 0 or that they are perpendicular to each other, but parallel to each other, but it's essentially because of the definition of the center of mass, that vc is a constant. It doesn't matter which point you're considering, so that gets out, and what you will end up with is an integral of rcq dm, and that by definition is 0, because that's how we define the center of mass. So from the definition of the center of mass, you see that the first term vanishes, only the second term remains. The second term involves a double cross product and involves an r on either side of omega, r being the position vector from the center of mass to the arbitrary material point, and omega being the angular velocity of the rigid body. That's not a function of the location of q, so omega can actually be taken out, but it's actually now juxtaposed between the two rcq's, so you can't directly do that as of now. So we will take this forward in the next slide. So this will become our starting point for that, and we want to eventually reach this expression for the angular momentum about the center of mass. It might look like it's kind of messy, but actually you'll see a pattern to it, and you will see one of the purposes of this exercise, as I said, was to introduce the inertia matrix, and you will see flavors of that already over here, right? So we ended the previous slide with one of the with the equation there. Let me just recap that. So we ended up with this. So we want to actually evaluate this integral. First of all, we have to evaluate the cross product within the integral, in order for which we need these two vectors. We need rcq, we need omega. So which is what we will start with in the next slide. First of all, rcq, that is the position vector from the center of mass of the body to an arbitrary material point q, and that position vector can in general be written in terms of any basis. We choose the basis which is fixed to the body, which is a body fixed reference frame. Therefore, because it's fixed to the body, we call it bi, which is bi hat, b1 hat, b2 hat, and b3 hat. and let's say the coordinate measures along those three are x, y, z. Remember, this is a position vector from the center of mass. So we would, yeah, and the b hats are unit vectors along the reference axis, which are fixed in the rigid body's frame of reference, right? Next, remember for that cross product that we want here, we have our CQ already in place. The other thing that we need is omega. We can express omega also in the same frame of reference unit vectors, and measure numbers for that turn out to be omega x, omega y, and omega z. So once again, I'd like you to recollect that when we talk of the product of the measure number with the unit vector, we call it a component. But when we talk of just the scalar quantity, which is the magnitude along a particular unit vector, we call it a measure number. And so we have to be consistent in what we call either of them. So now that we substitute both of these, the cross product is very easy to take. You've been taking quite a few cross products in your homeworks as well. When you do that, both the cross products, then you end up with the squares of x and y, z, or their products, and which is what you see in terms of y squared, z squared, x, y, etc. And you also have the omega as a linear term, because you see that omega appears only once within this integrand, and r appears twice, and therefore you see the squares of x, y, z, or their products appearing in these. So we're just expanding this particular thing and then collecting the coefficients of b1 hat in the first line, b2 hat in the second line, and b3 hat in the third line, so that you have the bi components of the angular momentum about the center of mass. So when you do this, you tend to see a pattern over there. If you take a look at the first element of the first row, second element of the second row, and third element of the third row, then you see that there is a sum of the squares of coordinates, whereas all other terms are products of coordinate measures, and which is what we end up calling as these terms. When we put it eventually in the form of a matrix, these three terms will lead to moments of inertia, these three terms, whereas all the other terms will lead to off-diagonal terms of that matrix, which we will call as products of inertia. And product is, the reason is very clear, it's essentially a product of two different coordinate measures of each arbitrary material point. Then of course you integrate over the whole thing. So we have not accomplished the integration, remember. All that we have done is substituted for the measure numbers of both the vectors that are involved within the integrand, and then expanded it out and again collected coefficients of about the three sets of unit vectors. That's all that we have done. So this integration can now be carried out depending upon the shape of that material and the mass distribution within that shape and the size of the material. So essentially the limits of the integration will be based on the size of the material. The mass distribution will give you how dm is distributed at different locations along the rigid body. It could be made out of multiple materials, so multiple densities might be, mass densities might be involved with the calculation. But the important point to note is that in all of these integrals you have one of the measure numbers of omegas, that is either omega x, omega y, or omega z. You see all of these have omega x, all of these have omega y, all of these have omega z, and that is something that's happening to the body, not to the point. So that can come out of the integral. So essentially what you have as the integral is just that, which is all we have already done. In fact, we have put the omegas after the dm to show that it's not, it doesn't matter whether it's within the integration or out of the integration, because it's a constant and there essentially comes out, and therefore the integrations are now of coordinate measures, their squares, either the sum of their squares or their products multiplying with dm, and therefore they lead to inertial properties. Okay, so that's essentially what we have carried out, the cross product, double cross product. Okay, so this is what we had at the end of last slide. This becomes the starting point for us in this particular slide, and these are the terms of the angular momentum as we already discussed, and the coefficients of the angular velocity is what we want to now look at coefficient of omega x you want to take out separately, coefficient of omega y separately, and similarly the coefficient of omega z, right? So when we do that, we give these names to these quantities. What we have on the right hand side here are the moments of inertia, and what we have on the left hand side here are the products of inertia. So, and remember that all of these are about the center of mass, because that's how we started defining the angular momentum, first of all, about the center of mass, and therefore the position vector that was of concern for us was RCQ, position vector from the center of mass to the arbitrary material point. We can of course find these inertial properties about any other point as well, which will be related to the angular momenta about that particular point, but the equation would not be as simple as what we see over here. So I go back to that statement that we made, that for an arbitrary material point, the arbitrary point about which you want to take the moment or the angular momentum, you would not have a direct relationship of the torque being equal to rate of change of angular momentum about that point, but for the center of mass that does happen even when the center of mass is moving. So even when translation is happening, which can be taken care of, as we said, by E1L, which is Euler's first law, which is for translation of rigid bodies. So what we have now here is a very, very important result, that we can write the angular momentum about the center of mass in terms of the moments and products of inertia about the center of mass. So in general, for an arbitrary shaped body, all of these can exist. In other words, they can have non-zero values, and therefore all of them need to be accounted for, right? And also based on how this has been derived, you can see also the importance of the negative signs over here. Sometimes people tend to miss that out, so just be aware of this. Okay. Now, therefore, that same result what we had in the previous slide can be written much, much more compactly with the new definitions that we have of these diagonal terms, namely the moments of inertia, and the off-diagonal terms of this matrix, which are the products of inertia. All that you have to do is just call that a matrix of moments and products of inertia, what we call as the inertia matrix about the center of mass, which is why you see a superscript C in all of those terms. And that is just going to multiply your angular velocity measure numbers, also along the same body fixed reference frame with the unit vectors b1 hat, b2 hat, and b3 hat. So remember that the omega x, omega y, and omega z are measure numbers along b1 hat, b2 hat, and b3 hat, which is along the same measure, along the same unit vectors that you have the angular momenta as well. So when you say hx, hy, and z over here, we are referring to the components of hc vector about along those three directions, b1, b2, and b3 respectively. Okay. So the angular momentum measure numbers along the rigid body axis, we are essentially writing it also. Remember, we wrote the position vector RCQ about b1, b2, b3, the measure numbers being x, y, z. We wrote the angular velocity again along b1, b2, b3, with the measure numbers being omega x, omega y, and omega z respectively. Similarly, we have written the angular momentum also about the same set of unit vectors, b1 hat, b2 hat, and b3 hat, to get to what you have on the left hand side of this, or the column matrix that you have on the left hand side of the last equation. And of course, here we've written it out explicitly in an expanded form, but many a times you just write it as I superscript C to refer to this 3 by 3 matrix as the inertia matrix about C in the rigid body axis. So it's also important in which axis you are expanding it out. Okay. So it's essentially, and unlike vectors, which you need to say that you need to expand in a certain basis, here it's a dyadic, or in other words, something which requires two sets of directions. So both those sets of directions in this case have been taken to be your bi hat system, which is why you have this simple form to that. and therefore you need to mention not only about which point this inertia matrix is, but also about which set of axes you are taking, and more often than not you would see that it's taken about the same set of axes on either side, which is why we say in rigid body axis, then it refers to both sets being bi hat. The previous slide, of course, we saw this is what we got in the previous slide. So now we see that the final result can be in words expressed as the angular momentum measure numbers, which is your hxc, hyc, and hzc, can be written in terms of the angular velocity measure numbers in the same set of axes, that is the rigid body fixed axis, and those measure numbers are, of course, omega x, omega y, and omega z. Okay. Now we get on to expanding that a little further and bringing in Euler's second law, because remember, all that we have done is now to go from the angular velocity to the angular momentum, or vice versa if we can invert that matrix. Now we want to get back to Euler's second law, which we already had in terms of the angular momentum. Now we have an expression for angular momentum in terms of the angular velocity. We just want to substitute that there, and therefore we can get to the same Euler's second law, but expressed now no longer in terms of angular momentum. We just said that the torque is equal to rate of change of angular momentum for certain specific points, namely the inertially fixed point and the center of mass. But now we want to do that rather than angular momentum, we want to do it in terms of the same rigid body's angular velocity, right? So now let's recap what we had for the Euler's second law. We just said that it's the torque equal to rate of change of momentum, and the momentum involved, of course, was the angular momentum, and this was valid for just 2 points, of which we take one case, which is about the center of mass. So it's the torque, this is the sum of all the external torques acting on the system about the center of mass, and that's equal to the, and this is very important because remember, Newton's laws were valid only in inertial frames, that is when the frame is not accelerating, by which we also mean that it should not be rotating, because when it's rotating the directions change of the velocity, and therefore it is in essence accelerating, and therefore it's very important to recollect that it was from Newton's laws that we derived the Euler's laws, because Newton's laws were for particles, and then we integrated over the particles that the rigid body is composed of, and therefore we got to the Euler's second law. So whatever assumptions were valid for Newton's second law remain valid for Euler's second law as well, which is that first thing is that it is in an inertial frame of reference, right? So now id by dt, of course, of the angular momentum. This is, of course, equivalent of the Newton's second law, where we said that the summation of forces was equal to the rate of change of the translational momentum. Here it's the rate of change of the angular momentum. Once again, the rate of change being measured in an inertial frame of reference. Okay. So now, just like we can do this for any vector, because we want id by dt, we can write it in terms of bd by dt, that is taking the time rate in a different frame, which is the body fixed frame, because remember, all the quantities we've been expressing with respect to b1 hat, b2 hat, and b3 hat measure numbers, whether it is rcq or whether it is hc or whether it's omega, we've been expressing all of them with respect to the bi hat system, and therefore we would want to express this as well, this equation in terms of the b system. And in order to do that, we have to move from the I system, which means that we take a bd by dt and then a term which is the cross product of the angular velocity with the quantity whose time rate we are interested in, namely angular velocity of b in I crossed with the angular momentum of the body with respect to the point C. Okay. Now we have all of these terms. All that we need to do is to go ahead and plug in, because we remember derived an expression for hc as I times omega in the previous slide. So all that we need to do is substitute that there, but both it's possible in general that I and omega can change. So you need to take that into account, especially important when you're dealing with rockets where there's a huge propellant burn, and therefore you need to take that into account. But otherwise, I remains constant, like we keep assuming mass remains constant, and therefore time rate of change of translational momentum was just mass into acceleration instead, is the assumption that we made. So we make something similar over here as well. The other thing that is important over here is now the cross product of omega with h, and that's going to complicate life a little bit, because remember we already saw h is nothing but I times omega. So now we are going to have essentially a quadratic term in omega. Okay, so in other words, this is going to become a nonlinear equation, whereas everything was hunky and dory with as far as the Euler's first law as well as Newton's second law for particles and system of particles are concerned, everything was linear, but now we will end up with certain nonlinearity, a quadratic nonlinearity to be more specific. You already see that in the result, but we have to get there in terms of a derivation. So we can represent the applied moment also in the same set of axes that we've been using for all other quantities, namely b high hat. So we express the torque, the sum of all the torques, external torques acting on the system, which is essentially a rigid body right now, about the point which is the center of mass of the rigid body, as these measure numbers mxc, myc and mzc along the b1 hat, b2 hat and b3 hat respectively, right? So that's as far as the left hand side of the top equation is concerned. Summation of mc is expressed in terms of its measure numbers, and then we already have the right hand side terms because we had hc as I omega, which we derived in the previous slide. We just go ahead and substitute, and this is the famous EDE, or the Euler's dynamic equations, as opposed to Euler's second law. So this is one form of Euler's second law, which is expressing the external torques in terms of the angular velocities rather than angular momenta. Then instead of calling it as Euler's second law, you end up calling it as Euler's dynamic equations, or EDE. And is a matrix equation, but when you expand it out into scalars, they are essentially three coupled equations, and all of them are non-linear, so that's important. So all are in terms of the rigid body axis. That is a simplicity there, of course, that everything is in terms of b1 hats, b2 hats and b3 hats. So it's kind of easy to juggle around with them, but you see that the second term involves omegas twice, and therefore there are quadratic terms in the omegas, which is what makes things a little more complicated. Now we can simplify this a little bit by choosing the set of axes b1 hat, b2 hat, b3 hat in an ingenious way. Essentially means that you're trying to make this matrix that is there, the inertia matrix, a diagonal matrix. What we end up with are known as the principal moments of inertia, and then the products of inertia vanish for certain specific choices of b1 hat, b2 hat and b3 hat. Already we have chosen a specific point, a special point to take the moments as well as the angular momentum, which is the center of mass. Now we also want to choose a special set of directions so that this can become a little simpler. We would still have the omega x squared, omega y squared and omega z squared, but we will not have the cross products, cross terms, and that's what would make this a little simpler. But nonetheless, it is a nonlinear ordinary differential equation that you have to solve. Ordinary because the only independent variable involved is time, which is what you see over here, and only the first order derivatives are involved. So it's a first order ordinary differential equation, making things quite simple from that perspective. The only complication being how do you handle the nonlinearities. Okay. Next thing you want to see is that there is an angular acceleration that can happen even when there are no applied torques. This is something strange for a lot of people in the beginning, because we are used to when there are no external forces, there can be no translational acceleration. That is something that we are familiar with, which is what Newton's first law actually tells us for us that a body which is in a state of rest or of uniform motion remains in a state of rest or of uniform motion as long as there is no external force applied. But here, even when there is no external torque that is applied on the system, you can still have an angular acceleration, a non-zero angular acceleration, which in turn, of course, means that the angular velocity can change. So in other words, it's like saying in the translational case, even in the absence of a force, a body can accelerate or a point or a particle can accelerate. In other words, its velocity can change, which is kind of violating Newton's first law. But remember, we're talking of entirely different animals over here, orientations, angular velocities, etc., which do not follow the same rules which the translational variables follow. Okay, so how do we get to this? We will see in the rigid body axis the same set of axes b1 hat, b2 hat, and b3 hat, right? So now, the previous slide, we derived this special form of the Euler's second law, which we called as the Euler's dynamic equations. So this particular equation we will take, and we will show that the even in the absence of angular momentum, applied torques, we can still have a non-zero alpha, right? Or in other words, omega can change. All that you need to do is to invert this equation in order to get your omega dots in terms of your omega, which all that you do is to take this term to the left hand side, bring the m's to the right hand side, and then you multiply by the inverse of the inertia matrix, then you end up with this particular equation. Now you see there are two terms to this. One, of course, you are familiar with. We're saying that the angular accelerations are going to be just given by the inverse of the inertia matrix multiplied with the external torques which are applied, which looks very, very familiar to the translational counterpart. But the new novelty that is coming with rotation is the second term that you have over here, which is saying that even when all of these m's are going to be equal to 0, the second term is going to contribute based on these terms that you have, quadratic in omegas, and of course again involving the inertia matrix. But once the this calculation is done within the brackets, you are of course going to be multiplying by an inverse of the inertia matrix, and you end up with in general non-zero values of omega dots. Okay, so we will continue from here after lunch.